Welcome to this Maths Methods 3 and 4 revision video on Chapter 8, Differentiation of Polynomials, Power Functions and Rational Functions. As is standard for this particular set, please note the questions and examples used in this video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook. No intention has been made to infringe copyright, and my apologies if it has. This is simply a video resource for my current students to assist in their preparations for their VCE examination. Thanks for any understanding you may be able to give. And so we start. Someone told me recently that looking at some of my videos, it's almost like I'm trying to reteach the topic rather than revise it. And actually, I probably would agree. However, I think maybe reteaching some of it, or at least keeping it fresh in mind, is as good as revision. So hopefully you're finding this interesting, if not somewhat time-consuming to watch. But on we go. Now, differentiation. So differentiation is probably one of the most misunderstood topics, in that when I went on university interview, I think I was asked what is differentiation, and having gone through sort of an hour and a half discussion, you went, yes, what you actually mean is differentiation is about finding gradients of points. And I sort of looked at him and I went, okay, and he went, what's integration? And I went, area under curves, and he went, much better. So I will never forget that actually when you are differentiating something, you are generally finding a function that will help you find the gradient at a point. From that gradient you can find equations of lines, you can find equations of tangents, you can find equations of normals, right? But the general idea is that it's about finding the gradient at a specific point, or a gradient function for a range of points. Now, one of the great things about differentiation is you're going to need to be able to use the idea of first principles. And this video is not going to even touch on first principles, but it will give a general idea. Imagine you have the incredibly dodgy graph, once again, of a curve. And on that curve, you have 2 points. We'll say this point here and this point here. Now, if we call this point P for some strange reason, and we find that point Q, then what I'm going to say is, well, if that's got an x coordinate, then its y coordinate is given by a function of x, right? And I suppose that's true because normally we know f of x equals, and there'll be some sort of function. So if I have an x, we can write this in terms of x comma function of x. And if we move a distance along, this, and we have, say, x plus h, right? Then what we're going to do here is have function of x plus h as my new coordinate. And by that I mean we've moved this way a distance of h. Again, don't ask why we use h. H generally stands for height, but anyway, we'll come back to that one slightly later. Now, we know what the gradient is. We can find the gradient between any 2 points because we know that gradient is equal to up divided by across, or in Australian language, rise over run. Okay, so rise over run. Well, we know that the rise is going to be the difference in the heights. So that is going to be equal to my f, x plus h, minus my f of x. These are simply just restating the y coordinates taken away from each other. And what about my run? Well, it's going to be my x plus h minus my x, which, if we notice, that x and that x cancels. And what we find out is that my gradient, right, between those 2 points is given by f, x plus h, minus fx all over h. And that formula there is actually pretty important. Why? Because what we find is, as this value of h gets smaller and smaller and smaller, what we find is we get closer and closer and closer to having the gradient at point P. And so we can now say that the gradient at point P, and we suggest that our gradient is given by f dashed of x, which we obviously all know now is the differential of x, is given by lim, and that means limit, as h tends to 0, of f x plus h minus fx all over h. Now that formula is incredibly important, and later on it comes into finding out, what would happen if you have small increases, and I think that's quite sexy again. But the general idea of gradients at points is based around this idea. If you have a function of x plus h minus function of x all over h, you can find gradients at points. One quick example, because undoubtedly there'll be one in an exam somewhere. imagine we have the function of x is equal to x cubed plus 2. Well, let's just look at what our formula states. Our formula states that f dashed of x is equal to lim, as h tends to 0, of f x plus h minus f of x all over h. So what it says is take your function and add h in, change wherever you see an x to become x plus h. So my function of x plus h will become equal to x plus h cubed plus 2. And we already know that my function of x is given by this, and we know that h is just going to be h, so I can now pretty much go and write in that my function of x, or f dashed of x, sorry, is given by x plus h cubed plus 2 minus my function. I'm going to put that in brackets so that we don't get any stupidity with signs. X cubed plus 2 all over h. Now if I multiply all of this out, and we can do this relatively quickly, I get x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2. Right, that's just this part here that's been expanded out. And if you're not sure how I did the x plus h all cubed, it's using the idea of Pascal's triangle. All right, so you've got 1, 3, 3, 1. You notice your x cubed values count down, and your h cubed values count up or down depending on which. And then we do minus x cubed. Oops, and there we go. See, almost tricked myself. Minus 2 all over h. Now, which gives me, so let's do some cancelling out, because I can see some cancelling I can do. There's my x cubed there, cancels with a minus x cubed there, a plus 2 cancels with a minus 2 there, and I think that's pretty much it. And what do I get? So I get 3x squared h plus 3xh squared plus h cubed all over h. What do I notice? I've got a h in every single term, so I can start cancelling h's as well. So that h cancels with 1 from there, 1 from there, and 1 from there, which gives me, f dashed of x is equal to 3x squared plus 3xh plus h squared. Now I'm going to put over here as the limit of h tends to 0. Well, what will happen as h tends to 0? Well, as h gets smaller and smaller and smaller, this term here will eventually become multiplied by 0. This term here will eventually become multiplied by 0. And what we find is that our differential is given by 3x squared. All right? So that's just a trick, or that's just an example on how to use it, as seen on pretty much every exam paper. However, the great thing with differentiation is that we can do that quickly, and just as a heads up, all right, and just as a reminder, if you've got x cubed plus 2 and you differentiate it, what do we do? Well, the general idea of differentiation is, or the shortcut if you will use it, is the power moves down in front and multiplies by what's ever in front, and you take 1 off the power. So this becomes function of x, or f dashed of x, is equal to, right, the 3 moves down and becomes x squared. What does this plus 2 become? Well, if you remember, that's the same as saying 2x to the 0. Why? Because anything times the power of 0 is 1. Now again, if we're going to follow our differentiation rules, that 0 multiplies by the 2 to give me 0, and it doesn't really matter what happens after that. And in a shortcut sense, a constant differentiates to 0. And there we go. We have our answer. Slightly quicker than using what we'll call differentiation by first principles, but it's something that becomes incredibly powerful as we move through. So if we have f of x is equal to 3x cubed minus 6x squared plus 1, and I want to find f dashed of x, what do? Well, I follow my rules. The power times by there becomes 9x, and 1 off the power is 2. 2 times the minus 6 is minus 12x, take 1 off the power is 1, I'm not going to write it, and a constant differentiates to 0. So we get function dashed of x. And what if I wanted to find f dashed of 1? What does that mean? Well, if you notice, maths is about comparison. So what do I notice? I've noticed that this and this are the same, but only x has become a 1. So in other words, let x be 1. So I get 9 times 1 squared minus 12 times 1, which is 9 minus 12, which is equal to minus 3. Et voila, f dashed of 1. And what about if I have a function of x is equal to 3x cubed minus 6x squared plus 1. And I want to find the gradient at the point 1 minus 2. Whenever they give you a coordinate, it's code. It's code for, hello, here's an x and a y value. You're about to use them later on, but here's an x and a y. It's code, big code, big code, big code, like Da Vinci Code, but not Da Vinci Code. Yep, hang on a moment. And so what do? Well, I can firstly differentiate it. Remember, what am I finding? Well, that's going to be 3 times 3 is 9x squared, minus 6 times 2 is 12x, and plus 1 disappears because it's a constant, not interested, so I get 9x squared minus 12x. Same question. Should have noticed. Never mind. So what do I find? Well, I now know that the gradient function is given by that. I want to find the gradient at that point. Well, what you notice is the y value is actually irrelevant. I don't need it, because when I differentiate, I'm only ever interested in the value of x, which in this case is once again 1. So having already done all the hard work by substituting 1 in, what do I find? Well, yep, I find that the gradient at that point, right, the gradient at that point is equal to -3. And I could write f dashed of 1 is equal to -3, which I did before, but it's neither here nor there. Now, what can I do with this gradient value? Well, there's all sorts of things I could do. I could actually find the equation of the line at that point. Right? I could find the equation of my tangent at that point. Why? Because a tangent is literally a point, a line that touches a point at a particular place. Well, if I know the gradient of this point here, I then know the gradient of the tangent. So please, big, big hint. The gradient at a point is equal to the gradient of a tangent. And if I know the gradient of a tangent, I can find the gradient of the normal. Because if you remember, the gradient of the normal is inverse and change the sign. So you take the reciprocal and change the sign. So that's pretty much all the information we need to know about differentiation in its basics. Does it work with negative numbers? Well, of course it works with negative numbers, right? So if I have function of x is equal to, I don't know, x to the minus 2 plus 3x squared minus 1 over x to the power of 4. There's a number of things here. Plus 6, we'll throw out a constant because we like constants. And, well, first things first, this is a trick. Fractions are a trick in differentiation. So what we do is we turn this all into negative powers. You can only differentiate negative powers if, you can only differentiate fractions if they become negative powers. So that become minus x to the minus 4 plus 6. And then we differentiate as normal. Right? So my f dashed of x becomes equal to minus 2x, take 1 off the power. Now this is where people get confused because they're not doing minus 1. But let's do minus 3. Right? So 3 times 2 is 6, or plus 6, x to the power of 1, not going to write it. Minus 4 times minus 1 gives plus 4 times x to the minus 5, and the constant disappears. And you could write this as minus 2 over x cubed plus 6x plus 4 over x to the power of 5, and the job would be done. So that would be my gradient function for that particular curve. Now, differentiation is an incredibly powerful tool, but what you've noticed so far is that I have had functions along the lines of x cubed plus x squared plus x plus a constant. All of these terms are separate and they just have one x in them. What happens when life gets more complicated? Well, that's where we use the tools provided by differentiation. And the first one of those is called the chain rule, and I love the chain rule. All right, I actually love differentiation. I think it's a very powerful and sexy tool. All right, you've got something pretty complicated in there. All right, you cannot at this moment differentiate that. Why? Because I don't have a row of x terms. Right? You might argue, well, I've got one inside a bracket. Can I just do it inside the bracket? No. And then you could say, well, I can multiply this out, and what would it get? And it's like, well, that's easy enough. I can multiply that out. Well, would I really want to if there's a quicker way? Well, you might argue that this isn't the quicker. Let's just check. Look, okay, I'm going to multiply this out. An x cubed plus 1 multiplied by x cubed plus 1. What does that give me? X to the 6 plus 2x cubed plus 2. All right, nice and easy. So if I now differentiate that, what do I get? I get 6x to the 5 plus 6x squared. Constant goes. Easy. Yeah? What though would happen if I had f of x is equal to x cubed plus 1 to the power of 30? Yeah? Don't know about you, I don't particularly want to try and multiply that out. Well, I could do, because I could use my chain rule, I could use my Pascal's triangle, and I could be going forever. But there's got to be a quicker way of doing this, and there is. And this is one of those things I say to all of the groups I've ever taught throughout maths, is with anything that looks complicated, take it out. And this is what I'm going to do. I'm going to say, right, let's come up with the general idea that y is equal to x cubed plus 1 squared. I'm going to get rid of this function of x business and start writing it in terms of y equals. This thing here is complicated. I don't like it. It doesn't look nice. So I'm going to let that equal the letter u. I'm going to take it out. I'm going to move it to a different part of my question. And what does that now make y equal? Yeah, y is equal to u squared. Well, the reason we like this idea of taking out the complicated thing is because I now have one basic term I can differentiate. So I can now say that dy by du is equal to 2u. That seems nice and easy. But that's not actually what we want. If you remember, we're looking for function of x, and we know that that's the same as dy by dx. I've got dy by du. What do? Well, what happens if I go over here and do du by dx? This is now nice and easy. This is easily differentiable. So I get 3x squared. So I've got a dy by du, and I've got a du by dx. Well, what you notice is that dy by dx is equal to dy by du multiplied by du by dx. Why? Because, and this is not great maths, but that du and that du cancel, and what do I get left with? I get left with dy upon dx. So yep, so that's literally what you do. You take dy by du, which is 2u, and you multiply that by du by dx, which is 3x squared. Well, my maths teacher probably would have slapped me hard with a number of implements in the classroom, including tables, because now we've got mixed letters, u's and x's, and you can't have that. Remember, dy by dx can only be in terms of x's. But we know what u is, so we substitute. So that's the same as 2 lots of x cubed plus 1 multiplied by 3x squared. And if we tidy all that up, what does that become? It becomes 6x squared multiplied by x cubed plus 1, or 6x to the 5 plus 6x squared. And what did we get previously? 6x5 plus 6x squared. Now you're probably sitting here looking at this video, if it's for the first time, going, and why would I? Is it not actually just quicker? That was 1, 2, 3, 4 lines of working against 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of working. Well, as I said, for this example, you possibly wouldn't use the chain rule. For that example, I would have a strange idea that you may be going at that for some time. So that's the chain rule. It works in terms of, negatives as well. So if I have y is equal to 16 over 3x squared plus 1, right, that's horrible, right? We don't like that. We're trying to find y dash. Well, there's the complicated bit at the moment, right? So why don't we let u equals 3x squared plus 1. I'm going to do du by dx is going to give me 6x, and there's part of my question. What do I need to do here? Well, I need to change that into terms of u. So that becomes 16 over u. And from previous differentiation, you can't have a u on the bottom, right? You can only differentiate when everything is up on the top, or a negative power. So that becomes 16 u to the minus 1. So I now know that dy by du is equal to negative 16 u to the negative 2, or minus 16 over u squared. So that's dy by du. And using the chain rule, we know that dy by dx is equal to dy by du multiplied by du by dx. And so let's just substitute it in. dy by du is minus 16 over u squared multiplied by 6x. I've got this mismatch of x's and u's, but I know that u was minus 16 over 3x squared plus 1 times by 6x, or in ninth parlance, what do we get? We get minus 96x over 3x squared plus 1. All right? I don't even know how we would actually differentiate that in any other way. All right? So in this case, the chain rule is lovely. This thing here is called the chain rule. It's about taking out the complicated stuff and making it easier. What about fractional powers? Exactly the same thing. If I had y is equal to the root of x, well, and I want to find y dashed, well, let me think, how do I do that? Well, we know that actually that could be rewritten as y equals x to the half, and from then on the rules happen in exactly the same way. We find that y dashed is equal to the half moves to the front, and you take one off the power, so that becomes minus a half. So if we think about that, that becomes a half multiplied by 1 over the root of x. Why? Because anything to a power of negative means you move it under set of, or move it to the denominator, and then that half means the square root of, and so that becomes 1 over 2 root x. Right? So whenever you have roots or cube roots or whatever else, raise it. Fractional powers work in exactly the same way. Just remember to take away 1, and please take away 1 in the right way. Okay? Some horrific mistakes happen when you have y is equal to x to the 2/3, for example. The number of times I see people do this wrong, right? So y would be equal to 2/3, or rather y dash would be equal to 2/3 x to the minus a third. If I've got 2/3 of a cake and I take away a cake, I've got minus a third of a cake, right? Not minus 2/3 of a cake. So fractional powers work in exactly the same way. So we've got the chain rule, right? That's when we've got one x term in some complicated places. What about if I've got stuff that's stuck together, right? And by that I mean, y is equal to 2x squared plus 1 multiplied by 5x cubed plus 16. Now again, you could say, well, that's okay, I can multiply, and use FOIL and maybe in this particular example it would be trivial and it would be easy to do, right? But let's just talk through the idea of the product rule. Now we've had the chain rule before. That's where we've got one x term, either inside a horrible bracket or below a fraction. Here we've got effectively two x terms, one there and one there. There's an x term multiplied by an x term. And that's the trick here. If you've got an x term multiplied by the x term, you can use what we call the product rule. Now the way I remember the product rule is that y is equal to u v dashed plus vu dashed. Right? And what does that mean? Well, you've got these two terms here. So we call one of them u and we call one of them v. So let's just look through this. Sorry, that should be y dashed as well. So y dash is equal to u times v dashed plus v times u dashed. Well, if I know that u is equal to 2x squared plus 1, then u dashed now becomes 4x. Right? So we've just differentiated. And if I know that v is equal to 5x cubed plus 16, I know that v dashed is 15x squared. And what does this little beauty say? It says literally multiply those corners together and then add them. Right? That will be our product rule. So that will give, so u was 2x squared plus 1 multiplied by v dashed, which is 15x squared, plus v, which was 5x cubed plus 16, times by 4x. And if we do a bit of manipulation, I get 30x to the power of 4 plus 15x squared plus 20x to the power of 4 plus 64x. And joining those together gives me 50x to the 4 gives me 50x to the 4 plus 15x squared plus 64x. Now again, you possibly could have multiplied these out and gone straight to where we needed to, but this was just showing the idea. You know what would happen, for example, if you had x cubed 3x minus 5 to the power of 4. That starts to get complicated in terms of trying to multiply this out, but again, what you notice is I've got an x term multiplied by an x term. So we use this product rule, and again, one of them's u, one of them's v. Work out what u dashed is, work out what v dashed is, and multiply the corners together and add the results. Right, that's the product rule. It's beautiful, love it. And obviously, if there's a product rule, there must be something else. Welcome to the quotient rule. What's the quotient rule all about? Well, if we had a function of x earlier where we had an x term multiplied by an x term, what do we do if we have an x term divided by an x term? Well, this is where we use our quotient rule. Now I'm just going to show you the product rule was given by y equals u v dashed plus v u dashed. The quotient rule is different, all right? Y is equal to v u dashed minus u v dashed all over v squared, all right? That's a v, by the way. So this is basically written backwards with a v squared underneath that, and you know, there's probably lots of ways of remembering how to get this formula here, but I just remember it that that's uv plus vu, and this is vu minus uv. I don't know why, but it works. So how does that work? Well, in exactly the same way as we did before. The top thing becomes u, the bottom thing becomes v, and we do the same thing. So if u is equal to x minus 2, u dashed is equal to 1. Why? Because that's 1 times 1, x, all right? X just becomes 1. And v is equal to x squared plus 4x plus 1. So v dashed becomes equal to 2x plus 4. What do we do now? Well, we just substitute it back into our equation there. And that should be y dashed, by the way. I keep missing the y dashed. So my f dashed of x becomes equal to, let's see, v, which is this. So v was x squared plus 4x plus 1 times u dashed, which is 1, minus u, which is x minus 2, times v dashed, which is 2x plus 4, all over v squared, which is x squared plus 4x plus 1 squared. Now, I wouldn't think you would be ever expected to multiply all that out, right? Leave the bottom as v squared, but you are expected to do the manipulation of above. So what would I have? I'd have x squared plus 4x plus 1, multiplying those out, minus, I'm just going to do this as a subcalculation, 2x squared plus 4x minus 4x minus 8 all over x squared plus 4x plus 1 squared, which is equal to, well, that plus 4 and that minus 4 disappears, so I'm going to get x squared plus 4x plus 1 minus 2x squared plus 8 all over x squared plus 4x plus 1 squared. I think my graphics tablet's now beginning to struggle. And let's see, what do we do? Well, I've got, now I'm going to end up with a minus x squared term in here, and convention says we normally don't put that first, but we'll go with it anyway. So an x squared minus 2x squared gives me minus x squared. 4x, I've just got one of those, one x term, so that stays as it is. And plus 1 plus 8 is plus 9, all divided by x squared plus 4x plus 1, all squared. And ladies and gentlemen, there is my answer. All right? So again, when you have an x term divided by an x term, and you can't do any quick and easy manipulation to turn that into a range of terms that just have x in, then you're going to be expected to use the quotient rule. Strangely, and I've not seen this outside Australia, you may actually be asked to do graphs of gradient functions. Right? Graphs of gradient functions. And the quickest way I think I can explain this, or just recap it, is if you have a function that is a curve, for example, right? This point here is the lowest value. We know that in a maximum and a minimum, the gradient is equal to 0. So at a maximum or a minimum, we know the gradient is equal to 0. That's really important. What do I know about all the gradients here? Well, on this side of the line, all of my gradients are actually negative. Why? Because if I was to draw a tangent at any point, it would end up having a downward sloping line. And what are my gradients on this side, or the gradients on that side, will be positive. Right? Why? Because again, if I was to draw a tangent at any of those points, I'd have a sloping line going up at various degrees, right? And remember, as they go up this curve here, the gradients would get more and more positive. Now if we were looking then at trying to draw that, and this is my graph of y against x, for example. If I now have to try and draw that in terms of a gradient function, well, what we would notice is this point here, remember, whatever that value is will have a gradient of 0. So that's one of the easiest ones I can draw. There we go. Assuming that these are sitting underneath each other, this would have a gradient of 0. A negative gradient. How do we show a negative gradient? Well, where are our gradients? This here is our y dash, and this here is x. Well, what do all the values under this part of the line, under the x-axis mean? Negative. Congratulations. And what about the values going above? Positive. Congratulations. So what we actually draw, I know it sounds a bit bizarre, is a straight line. Right? This graph here would have this gradient function here. Remember? Positive, increasing positive. There we go. There's positive, increasing positive. Decreasing negative. There we go. Decreasing negative. 0, 0. Seems quite exciting. Yep. And one more example, which is a cubic. For example, let's look at what the important points are. Now again, a maximum will have a gradient of 0, a minimum will have a gradient of 0. So I'm going to draw underneath here. So I know that this point here will have a gradient of 0. Let's change pen. And this point here will also have a gradient of 0. Well, that's interesting. How on earth is this thing going to cross twice? Well, look, what do we know about all the gradients on this part of the graph? This part of the graph, yes, they're all positive. What do we know about the gradients on this side? Yep, negative, and the gradients on this side, they're all positive. But what you notice is these get faster and faster and then they get back. So I've got to have a positive, a negative, and a positive. So that means I've got to have a gradient above the line, doing this. I've got to have a gradient below the line, and I've got to have a gradient going above the line, all right, getting steeper. So again, it's hard to explain, but these here are getting smaller and smaller and smaller. And these things here will be getting bigger and bigger and bigger as we got there. So getting bigger and bigger and bigger must be that. Getting smaller and smaller must be that. And again, these will go down to and there. So what we notice is that this will actually do that. So that's my f dashed of x, and that is my x, and this is my f of x, and this is my x. So I always look for where the gradients are 0, put them on, and I put this positive, negative, positive on, and then I work out, well, the positive have got to be above the line, negative have got to be below the line, and how is the only way I can join this together? Yes, exactly the way it's just been shown. Right, so that's, again, a quick recap of gradient functions. Something that seems to come up ever so a lot is the idea that if you have the function of x is equal to modulus of x, how on earth would you differentiate that? How would you differentiate the modulus of x? Well, that's exactly the same as x when x is greater than or equal to 0, or minus x when x is less than 0. What we find out is when you differentiate that, what do we get? Well, the difference of x is equal to 1 and minus 1, which would suggest that actually the value of x equals 0 is discontinuous. We'll come back to that, the idea of discontinuous shortly. So that's actually only true for x is greater than 0, and that is only true for x is less than 0, and there is no definition when x is 0. Right? There is no differentiation when x is 0. Right? So we say it's not defined. So we now know then that f dashed of x, or the modulus of x, is that, and that's going to come back to being quite important, right? We'll meet this again shortly. But if you now look at the textbook, it seems to go on a little bit about discontinuity. What is discontinuity? It's basically where a graph breaks, or it doesn't fit in terms of a function for the whole length of the line. So for example, if I have the graph y equals x squared, we know that I can draw that, and we're going to end up with something looking pretty much like that. There's no break in the graph, there's no value it doesn't work for, but if we had a graph looking like this, for example, then there is a most definite discontinuity. There is something not quite right about this point here, okay? So this graph and this graph are joined by some sort of functional rule, but they don't actually join in terms of the actual equation. So a discontinuity may be shown, or a function may be shown, something along the lines of function of x is equal to 2x for x is greater than or equal to 0, and minus 2x plus 1 for x is less than 0. Now, how do we find out whether this graph is continuous or not? Well, as far as I'm concerned, this value here is the important one. It's almost like a flashing beacon to say, well, look, what happens if I put x equals 0 in here and x equals 0 in here, right? Because as this graph approaches 0 and as this graph approaches 0, what are the values going to get closer and closer to? Well, okay, when x is 0 here, what do I get? Well, I get 0, but what do I notice here? I get plus 1. So what we tend to notice is that this graph here will look something along the lines of, well, for x is greater than or equal to 0, the graph of 2x we know is going to look something along those lines, but for this here, minus 2x plus 1 is going to look something like this. So, yep, that would suggest that there is definitely a discontinuity. So that would be a circle, and that would be a filled-in circle. Why? Because that's x is greater than or equal to 0, and for x is less than 0. So there is a discontinuity when x equals 0. And realistically speaking, to be honest with you, I can't see too much more else in this with regards to discontinuity. I'll do one more example. So if we had, I don't know, f of x is equal to of x squared plus 1 and minus 2x plus 1, and we have x is greater than or equal to 0 again and x is less than 0. Well, this is pretty much saying put in your values of 0 and see what happens. Well, if I put 0 in here, I get plus 1. If I put 0 in here, I get plus 1. Is there a discontinuity? Nope. Why? Because although the functions seem to differ, they are pretty much joined, right? There is no gap in between my functions. So x squared plus 1 for x is greater than 0 would look like this, right? With a dot, and minus 2x plus 1 would look like this. They were joined at the same point. They could both be 0, as it were, and there we go. So there is no discontinuity. Really isn't too much more else to be able to say than that. We've already met previously the idea of the function of x of mod x can differentiate to give f dashed of x is equal to squiggly 1 and minus 1 for when x is greater than 0 or x is less than 0. And the reason this is x, by the way, is because that's the modulus function in there. How can we use this practically in a real example? Well, imagine, for example, we had the graph of function of x is equal mod of x squared minus 1, and I want to find f dashed of x. Well, the first thing is that looks rather complicated. I've got a modulus, so what I'm going to do is I'm going to actually use my chain rule, and I'm going to take this outside, and I'm going to say, well, let u is equal to x squared minus 1. So du by dx is equal to 2x. This now becomes y is equal to the mod of u, and we know that dy by du is equal to 1 and minus 1 for where u is greater than 0 and u is less than 0. But I actually know what u is, all right? Remember? I'm going to think of that in terms of x squared minus 1 is greater than 0 and x squared minus 1 is less than 0, right? Because that's effectively what u is. So using our chain rule, we can now find out that dy by dx is given by dy by du, this one, times this, all right? But I'm going to write it as 2x multiplied by the squiggly 1 minus 1 for when x squared minus 1 is greater than 0 and x squared minus 1 is less than 0. And you can just multiply that so that you get dy by dx is equal to squiggly brackets 2x when x squared minus 1 is greater than 0 and minus 2x for an x squared minus 1 is less than 0. And if we were to draw that graph very quickly and a sketch, what would we find? Well, x squared minus 1 would look like this. And where would my crossing points be? Well, there'd be minus 1 and 1. So we could now say then that that is true of 2x and minus 2x for the values when x squared minus 1 is greater than 0. It's that value there and that value there. So that would be that x is less than at negative 1 or x is greater than 1. And what about here? Well, it would be true of minus 1, x 1. Right? So my differential function of x squared minus 1 is literally given by this thing here. All right? So using the chain rule is quite important. What about another example? So one last example. What if I have the function of x is equal to the mod of x squared minus the mod of x? Well, the chain rule works in exactly the same way. So what I'm going to do is I'm going to say, well, let u equals mod of x. And I know that du by dx will now equal to blah, blah, 1 minus 1 when x is greater than 0 and when x is less than 0. And that now gives that y is equal to u squared minus u. So dy by du is equal to 2u minus 1. And so my chain rule now states that dy by dx is given by 2u minus 1 times 1 minus 1 for when x is greater than 0 and x is less than 0. And dealing with our mismatches of u's and x's, what do I know? Well, that becomes 2 mod x minus 1 multiplied by 1 and minus 1 for when x is greater than 0, x is less than 0. And we can, I'll put that in brackets and do a little multiplication and write that as 2 mod x minus 1 when x is greater than 0, and multiply these two together gives us minus 2 mod x plus 1 for when x is less than 0. And finalizing this, because we can, what does that mean? It tells us then that f dashed of x is equal to, because of this x is greater than 0, we can look at this value here and know that 2x minus 1 then for x is greater than 0, and likewise negative values make sure that that becomes 2x plus 1 when x is less than 0. So the chain rule is now helping us work out how to deal with moduluses and, to try and find derivatives of. Seems like quite a sexy way. And so that's been a pretty swift view of the differentiation of polynomials, power functions and rational functions chapter. I hope some of it's been of use. We'll see you next time for applications.